Hello, my name is Nikhil Subramanian, registration number 18BEC0711 of slot C1 serial number 52, and I'm here to present my DA1. The IC I have chosen is NVIDIA Caramel ARM V8. ARM stands for Advanced RISC Machine. So I've chosen NVIDIA Caramel ARM V8 because of its recently released AI computer, which is called as the Jetson Xavier NX. This AI computer uses this particular IC as its processing core. So first question, draw the clear block diagram of microprocessor or microcontroller IP core selected. For this, I've used Word document, the tools from the Word document to construct this diagram. It took the uses of box and text box, diagrams box and text box. And for the second part of the question, I found out the images of the internal circuitry on the NVIDIA websites for the CPU core which I have chosen. And then the CPU internal diagram was drawn using the YED tool. YED tool where I could draw the whole block diagram or flowchart of the entire CPU internal diagram. So number of instructions in the microprocessor. This microprocessor is very similar to the ARM A64-bit instruction set. There are almost there's 36 instructions here, and there are more move and store instructions other than that. So it's 36 plus 12 instructions totally for this ARM architecture, 64-bit architecture. Other than this 36, there are other register flags, almost 32 register flags, 32 bits of register flags, out of which 0 and 4 bits is for the processor mode bits, 5 bit 5 is for the thumb state bit 6 is for FIQ, bit 7 IRQ, and so on. Explain the microprocessing element architecture. The ARM V8A, which is used by the NVIDIA Caramel ARM V8 architecture, the later generation ARM architecture targeted at the application A profile. It introduces the ability to use 64-bit and 32-bit execution states known as ARC64 and ARC32. These are the instruction sets, ARC64 and ARC32, but this is predominantly ARC64 supporting. The ARC64 execution state supports A64 instruction set, holds addresses of 64-bit registers, and allows instruction in the base instruction set to use 64-bit registration for their processing. So the ARM V8A architecture allows different levels of ARC64 and ARC32 support. For example, ARC64 is used only for designing, and these designs also support ARC32 operating systems and virtual machines. ARC64 also supports with ARC32 at unprivileged application level only. And some other features of this ARC64 are branch target indicators, pointer authentication code, memory tagging extension, large physical address, 64-bit virtual addressing, automatic event signaling, larger register files, efficient 64-bit immediate generation, large PC relative addressing range, and additional 60 KB and 64 KB translation granules. Now to correlate between the ARM and the 8051 studied in Model 1 and Model 2. 8051 is an Harvard architecture, whereas ARM is a von Neumann architecture, which basically means that in 8051, separate memory spaces for RAM and program memory is given. But in ARM, RAM and program are in the same space. ARM has a 16 or a 32-bit architecture, whereas 8051 has an 8-bit architecture. 8051 has a limited stack space, which is limited to 128 bytes for 8051, whereas it's not the same case in ARM. 8051 and ARM can directly address all available RAM. 8051 need multiple clock cycles for instructions. ARM executes most instructions in single clock cycle. ARM has the best compiler and application support including free GCC compilers. Register organization. The architecture ARC64 has a 31 integer registers. There is also a stack pointer and a zero integer that always contains zeros. There are generally three types of registers. General purpose register, which most A64 instructions operate on. The architecture provides 31 general purpose registers. Each register can be used as a 64-bit X register, X, which means X0 to X30, or as a 32-bit W register, W0 to W30. These are two separate ways of looking at the same register. The example of this X and W is given below in this diagram. The second type of register is a system register. This and the general purpose registers define system registers. System registers are used to configure the processor and to control systems such as MMU, Memory Management Unit, and exception handling. System registers cannot be used directly by data processing or load store instructions. Instead, the content of the system register need to be read into an X register and operated on and written back to the system register. Then the third is the other registers. The third type are zero registers, ZXR and WZR. Always read as zero and ignores write. There is stack pointer as the base address for loads and stores, and stack pointer with a limited set of data processing instructions. The program counter, however, is not a general purpose register in A64, and it cannot be used with data processing instructions. So the algorithm used for signed and unsigned calculation. ALU is pretty much the same. The ALU has 32 bits input. The first comes with the register file while the other comes with the shifter. ALU's outputs modify the status register flags. The V bit output goes to the V flag as well as C out goes to the C flag. While the most significant bit actually represents the S flag, the ALU output is NORed, which means put through a NOR gate to get the Z flag. The entity representation of ALU is given in the figure attached to the document, which has two inputs, both a 32-bit with a C in from the bottom, which gives a V, an output of 32 bits, and a C out. This ALU has 4-bit function bus, which is Fin, given in the diagram, allows up to 16 opcode to be implemented. The first kind of multiplier used in this is booth multiplier. The booth multiplier has 32-bit input, all the inputs of the rest in the register file. So in the diagram, it's seen that there are three inputs, each of 32-bit, and the start and accumulate A register and the clock. And outputs also 32-bit after combining all three inputs and the function bus. Then comes the barrel shifter. Barrel shifter. This is basically a shifter which shifts the inputs left or right. This also takes in a 32-bit and gives out another 32-bit. Excess will be if there's an excess key bit which is shifted out of the 32-bit, this will be stored in the carry flag. Find what type of control logic used and correlate its performance with 8051. So control logic used in ARM is like a state machine. The processor timing is also included in the control unit. Signals from control unit are connected to every component in the processor to supervise its operation. However, in A051, the cycles of phases are constructed as a state machine, similar to ARM. The individual instruction executions can be constructed as state machine. The main difference lies in the fact that the 8051 does individual instructions, whereas ARM does multiple simultaneously. The rest all is pretty much the same. The difference between in MMUs between 8051 and ARM V8. This is generally used for bulk memory operations, both read and write operations. This is done by ARM V8. The ARM architecture forbids speculative reads of any type of device memory. Locations of the memory map are assigned to peripherals are usually assigned the device memory attribute. The device memory has additional attributes like they prevent aggregation of reads and writes, they preserve the access order and synchronization requirements, and they indicate whether a write can be acknowledged other than the endpoint. The implementation of memory depends heavily on the microarchitecture, and therefore many details of memory states are implementation defined. ARM-way defines the application level interface to the memory system, includes a hierarchical memory system with multiple levels of cache. The ARM memory model supports generating an exception to an unaligned memory access, restricting access to application to specify data to memory, translating virtual address provided by executing instructions into physical address, altering the interpretation of multi-byte data between big endian and little endian, controlling the order of accesses to memory, controlling caches and address translation structures, and synchronizing access to shared memory by multiple PEs. Elaborate pipeline and parallel processing capabilities of the unit and management techniques. Hazard management techniques. Hazards here are created mostly by uh, memory confliction or overheating due to too much of data transfer. The process of fetching an next instruction while the current instruction is being executed is called pipelining. Pipelining is supported by the processor ARMV8 to increase the speed of program execution. Increases throughput, that is. Several operations take place simultaneously rather than serially in pipelining. The pipeline has three stages: fetch and decode and execute. The three stages used in pipeline are fetch. In this stage, the ARM V8 processor fetches instructions from the memory. Decode. In this the processor recognizes the instruction that has to be executed. Execute. In this stage, the processor processes the instruction and writes the result back to the desired register. If these three stages of execution are overlapped, we will achieve higher speed of execution. This exists in ARM V8 processor. Hazard management techniques. There are several main solutions algorithms used to solve data hazards. Three of which are inserting a pipeline bubble, operand forwarding, out of order execution. Under out of order execution, there are two more algorithms: code boarding and Tomasulo algorithm. To avoid control hazards microarchitectures, To avoid control hazards, microarchitectures can insert a pipeline bubble, or use branch prediction and essentially make educated guess about which instruction to insert. In which case, a pipeline bubble will only be needed in case of incorrect prediction. Memory latencies are another factor for designers must attend to, because the delay could reduce performance. Different types of memory have different accessing. Find whether processor level parallelism is available in the element selected. Illustrate cache, coherence, and protocol used for the handling memory hit or miss. Bit-level parallelism is a form of parallel computing based on increasing processor word size. Increasing the word size reduces the number of instructions the processor must execute in order to perform an operation. On variables whose sizes are greater than the word length, from the advent of very large scale integration, VLSI computer chips fabrication technology in 1970s until about 1986. The advancement in computer architecture were done by increasing bit level parallelism, as 4-bit microprocessors were replaced by 8-bit and then 16-bit and then 32-bit microprocessors. This trend generally came to an end with the introduction of 32-bit processors, which are standard in general purpose computing for 2 decades. 64-bit architectures were introduced in the mainstream with the eponymous Nintendo 64 in 1996. But beyond this introduction stayed uncommon until the advent of 86 to 64 architectures around the year 2014 for mobile devices with the ARM V8A instruction set. Hence, ARM V8 supports parallel processing, processor level parallelism. To detect hit and miss, ARM V8 uses MOLC protocol for the hit and miss detection. Other forms of protocols are using attack techniques like flush and reload, or flush and flush utilize the unprivileged 86 x86 flush instruction called CL flush to evict the cache line. Thank you.